volts. Every conductor is in a steel pipe this big around with shielding gas pumped in around it, so it won't arc to the pipe. All the pipes are grounded. So the substation is like, it's big, but literally I have a picture, like they told us, please don't touch anything, but once we got into the substation, I'm like, take a picture. And I'm hugging 500,000 volts. It's literally this far from my face in this pipe. So cool.
What kind of gas?
Sulfur hexafluoride, the most insulative gas on Earth when it comes to electricity.
Non-conductor, I guess.
Sulfur hexafluoride, SF6. It's an extreme ozone depleter. That's really, really bad for the ozone. But any power generation company will be quick to tell you the largest consumer of SF6 on Earth is not for power generation. It's Nike. Nike Air shoes, SF6 gas, that's what's in the pockets. It's inert and it has really, really low expansion contraction rates. So cold to hot, same cushion the whole time. That's where most of the SF6 gas that gets released in the atmosphere comes from, Nike Airs. Really interesting stuff I'm learning from people when we talk to them. But it was absolutely fantastic. They do an engineered lift there when they pull the rotor out of the alternator, so that part right there. And coincidentally, what we're about to talk about right here is the exact same rotor in an alternator. It's a synchronous motor one day, and the next day, it's an AC alternator. It is the exact same machine. The rotor, that piece cannon, is an engineered lift. What that means is they take both of their overhead cranes and they put them side by side and they hook a spreader bar between them and they hook onto that rotor. And those cranes say 300 ton on them. They are at the extended engineered safety feature. So when they put in a safety tolerance, they build it 5 times stronger than they rate it. They're at the actual build spec. So it says 300 ton and they're lifting 600 ton. Everybody has to evacuate the building when they pull that rotor out of the alternator. And there's only one spot they can set it down. It's a big red square on the floor. If they set that rotor down anywhere else in that generating floor, it will go right through all the concrete, right to the bedrock, because it's so heavy. So they have to set it on the red square, one rotor at a time. There's only 4. The entire Peace River goes through 4 turbines. And you're like, wow.
They have the same thing in the Brazil dam.
Mm-hmm.
Because at one time, if the dam's low, they're pumping up into the reservoir,
Yep.
it's high, and it's generating, so if you're.
And off-peak hours, they'll do a pump reservoir, so when you're not using power, then they'll take the grid power and just push it back up. Really cool.
They're recycling the water.
Yeah. But it costs electricity to do it, right? But you're still using grid to do it.
There's no free lunch.
That's right, no free lunch. It's exactly it. It's everything's gonna cost you. Pay me now or pay me later. I tell everybody that when I wire their house. Pay me now or pay me later. At the end of the day, it's a certain cost. We can skip all of that right now, and you're gonna have me come back 6 months from now and fix it all. But we can just do it now. It's the same cost either way. So it's kind of cool. This is the part that's really interesting. That does not change. Every 3-phase motor, that does not change. It stays just like that. The stator is the stator. It's the rotor designs that change. So when we move over to that cool thing, the synchronous motor, what I've got drawn looks a lot like this one. Looks very similar to it. The one noticeable feature difference that I haven't drawn yet, I'll put it there in a minute, is the fact that, see these rotor bars? They're tiny. They're not very big at all. They actually have a special name. They're so small and wimpy. They're called amortisseur windings. I always tell people it's like the French. They're small and wimpy. No. It's an amortisseur winding, also called a damper winding. You can hear it 2 different ways. But that little winding they're talking about is exactly the same as what a rotor bar does. So when I have a synchronous motor, and I draw it inside this stator, I'm going to draw the same thing I did before. Here's my bearing. Now I've got a little tiny rotor bar right there. Just a little guy. And a whole bunch of them. And when I turn on this stator field by applying this voltage, it goes through the exact same process as the squirrel cage induction motor. It does the exact same thing. So it comes up to almost synchronous speed. Still has to have slip, we know that, we've established you gotta have slip for it to turn. So it will accelerate, it will come right up to speed, but there'll be like a 5% slip. It won't be 3,600, it'll be 3,460. So it's almost going as fast as this stator. But it's got that cool term called synchronous. It's the next part that's ultra cool. Along with that principle of a squirrel cage induction motor That's just to get it up to almost synchronous speed. That's to accelerate it up. And we do that with no load on it. You cannot have this loaded, because as we know, when I slow it down, there will be more induced voltage on that bar and more current flow happening, and they're so small and tiny, they burn out. So those little things are there to get it almost up to synchronous speed. So we've accelerated it. Before we put load on it, we then have to synchronize it. This is the part that's cool. Along with the same structure with tiny rotor bars, that rotor also has an electromagnet built into it. So I'm just going to draw basically a cross section. There's that rotor cut in half. And inside that rotor is also a magnet. Now I'm drawing this simply. The magnets would match the poles in here. If this has 20 poles, that'll have 20 poles as well, but we're just gonna go north-south. Inside it is a magnet, just like this, north-south. That's not a permanent magnet, it's an electromagnet. And so for me to actually turn that magnet on, I will have windings of wire come in here, wind this thing, and come out. Now we gotta remember, that thing is spinning at 3,400 or 3,500 RPM, so that winding has to come out. Well, it's got to go through something really cool. It's going to have slip rings and brushes so that I can get voltage in, positive, negative, just like that. I need some way to put voltage into the middle of that thing. But here's where it gets really cool. Thinking back to our very first drawing, magnetic field, then a magnetic field, then a magnetic field. If I have the ability to take the rotor and suddenly install something in it that looks like this, where I have a magnet and a magnet that's part of the rotor, and I'm able to make this a south pole and this a north pole at that moment in time, what we have taking place is magnetic coupling here, magnetic coupling here, as in that north and south are sticking together. They're not touching, but they're sticking together. Well, what do you think happens when it goes from here to here? It follows it exactly. The rotor then goes, oh, it's that guy over there that's now the North Pole, not this one. It goes to there. Then it goes to there. Well, how fast do you think it's going to do that?
600 times a second.
At the exact same speed at which that stator field is moving. It hangs on to it the whole time. Now I've got an electromagnet in the rotor that hangs on to the electromagnet of the stator, and when the stator moves, the rotor moves at exactly the same speed. Hence the term synchronous motor. It will turn at synchronous speed. It turns at the calculated speed. Whereas a squirrel cage will never turn at the calculated speed. It's always going to be 5 to 15% less than that. So the synchronous motor all of a sudden turns at 3,600 RPM. That's pretty simple, isn't it?
Wow.
I mean, that is what happens. It's like, man, that is so easy. That picture in there is an absolute embarrassment to the electrical training. I just looked at it, I'm like, you don't get anything from that picture. It's a winding and a winding. You're like, what the hell is, where is this thing? That's where it is, right in the middle. And the cool part is, when I load this up, we have what's called tearing out of synchronization. And you can absolutely hear it when it happens. You got a motor that's running, it's like, as you load it up, it's like, when you break this magnetic field from this magnetic field because you put too much load on it, suddenly it goes, and your gauges are all over this. What the hell is going on? That's overloaded. It's like, no. Take the load off, you've overloaded it, you've broken it out of synchronization. And when that happens, these little mortise are winding, those little rotor bars, they're trying to carry the weight. They're trying to actually do the work. They can't, they'll burn out. So the whole reason that those little tiny mortiser bars are there in the first place is if I turned on this magnet in the middle, and then I instantly turned on this magnet going 3,600 RPM, this will never catch up. It's like, it's trying to catch up, that's going way too fast around the outside. So we have to get it close, so that then when we turn this on, it just gotta move a bit, and once it locks on, it's almost the same speed anyways. So back to the relay race. You imagine if the second runner in the leg isn't moving at all. They're standing totally still. Usain Bolt comes running up, going 47 miles an hour, and he's gonna hand the baton to somebody that's not moving at all. How effective do you think that'll be? That baton hits the ground every time. You never finish a race. That's why we gotta speed up the rotor. Smooth transition. Now you can connect. And away you go, synchronous speed. And so we love these things in the electrical world for a couple of reasons. Number one, a synchronous motor driven from a variable frequency drive, you know exactly how fast it's going. The squirrel cage motor doesn't do that. You have a VFD that's changing the speed. You can run a motor at 30 hertz instead of 60, and you can say it's going half as fast at 30 as it is at 60, but the slip increased on a squirrel cage, so you don't really know how fast it's going. That, 60 hertz, 3600 RPM, run it at 30 hertz, it's exactly half of that. Run it at 1/3 of the hertz, it's exactly 1/3 of that. It is exactly the RPM of the frequency that you feed it. So now for finite control, really, really important control, synchronous motors are the best, because you know exactly how fast it's turning. You know that if it's turning 250 RPM, that is 75 linear feet of conveyor speed. That's what we need for this production number. Suddenly you know exactly numbers. You can actually calculate off of it. Squirrel cage you can't. But squirrel cage is cheap and easy, so we use them all the time. Now with that synchronous motor, there are two rotor designs, and I did see that, so we're gonna talk about them really quick. If that thing is going to go that fast, that's really, really, really fast for a motor to turn. Rotor design changes a bit. If you're talking 3600 RPM, you're talking about a cylindrical rotor. What that means is the rotor is small in diameter and long because it's spinning fast. We don't want a whole lot of centrifugal forces way out here because it's spinning real fast. So we keep it nice and tight, magnets on a long line, that locks onto the stator and away it goes. That's for high speed. But for low speed, which is actually a lot of the stuff we do for low speed, you're turning that thing, well, I'll give you an example, Peace Canyon Dam. I didn't mention that just because I thought it was cool. It actually is part of this little lesson. Peace Canyon Dam turns at 58 RPM. That's what the rotor turns.
58.
5.8. You could watch the nick on the shaft go by. The shaft is 14 inches in diameter. That's between where the water turns it and where the rotor spins. It's this big around. You can watch a nick on the shaft go by. It's like, yeah, that's actually less than, or a little more than a second to come around. 58 RPM. It also means it's like from here to that window in diameter. That's called a salient pole. Low speed, salient pole. So that's when you're down to like 58 RPM. Salient pole.
So what did they call it, salient?
I don't know why they use the word salient, but when they put that pole in there, you literally have a rotor with poles that protrude off of it, and those are wound. And so it's like a single, a single, a single, a single. It's like, I don't know, salient probably is back to some definition in English, but it truly means an extruding pole, as opposed to windings in a rotor that's turning really fast. And so in the book, on page 4-23, they've got a salient pole rotor. That's 1800 RPM, that's cool. As soon as you're moving into 3600 RPM, you'll go to a cylindrical rotor, which I don't think they even show a picture of or really talk about, but there are two rotor designs. Low speed salient, high speed cylindrical. It's literally just dictated by the RPM in which it turns. That's it.
So they're still round.
Yep, it's still round. The salient poles are kind of cool though, because instead of being small and long, they're short, big in diameter. So it's like, oh, okay, it's like, I don't need to have something really long to get a bunch of magnetism on it. I've got these poles that protrude out like this, and so it's like a pancake that actually is short but large in diameter. And hydroelectric uses most of the salient pole and they lay flat, so we turn it this way. And it's usually the covers over it. It is the floor of the generator floor. It's like the covers are the floor, and underneath it is 400 tons of rotating mass. You're like, good Lord, that's awesome. Totally awesome.
Have you seen the rotors for Site C Dam?
Yeah. Smaller.
8 meters.
Yeah. Yeah, they're big. They're big. They're not huge. When they did Site B, Peace Canyon, those are the largest water runners ever installed in the world when they put those in. And if you go to that dam, it's really cool. everything that's water, everything that contacts water, made at the Kravsky Ironworks, Soviet Union. That's where all of it was made. It's all Soviet Union. And anything that electrons flow through, Hitachi, Japan. This down, there's an electron that leaves it that doesn't go through Samsung components, South Korea. Every single thing there is Samsung supplied as far as electricity goes.
Well, Samsung was one of the partners in PRHP.
Totally, that's why. So they came here, they had a whole bunch of mucky mucks come here in really expensive suits, and I think they wrote us a check for $875,000 when they walked away to the college to help support their electrical stuff. So it's pretty cool. I met a whole bunch of South Korean electrical engineers, really, really smart people, really smart people. Like, yeah, I know my motor theory, but I'm actually allowed to work on that. And they aren't, because they're engineers, so it's kind of cool. You know, they do the design, I do the construction and the maintenance. There's only one more thing that Will had asked me to add, the skewed or angled rotor bars. So you notice my rotor bars, I've drawn them all as a straight line, right? Well, in effect, when we built a squirrel cage motor, after we started building them and we got better at sort of understanding how they work, it kind of made sense to then take that rotor bar and not have it go directly across. This will be the same with those little mortiser windings too. It's just rotor bars. If we were to take that rotor bar, instead of going straight across like that, we ran it at a bit of a skewed angle. And they're all running like this, right? Like not just one, all of them are at that skewed angle. All we gotta think of now is when I have this in the magnetic field and the magnetic field is moving by it, instead of inducing voltage on the entire rotor bar at the same time for its entire length, if I turn it a little, I induce voltage, I'll turn it this way, I induce voltage right here first, and as the field moves past it, I'm actually inducing voltage at a different time for the length of the rotor bar. It, in effect, gives us a smoother thrust. It's like having helical cut gears in a differential versus bevel cut. And so we do this sort of skewing of the rotor bars so that it prevents what's called cogging. Because you can have skew them like that, it's smooth. The thrust happens along the length of it over time instead of on the length of it at one time. And so that's why we angle it. It's literally for smoother operation. That's it. No other special feature there.
And that's for both?
Yes.
So when you.
Not so much in the synchronous though, because we only use those for literally 2 seconds to get it started up.
Right.
Once it's synchronized, they're not playing. Once it's synchronized, remember, it's turning the exact same speed, there's no induced voltage on those little bars. Nothing's happening. There's no relative motion between them now, if this is going the same speed as this in a synchronous motor. It's pretty cool.
So on a synchronized motor, there's not really any slip, there's no slip.
There's zero slip, zero slip. The percentage is zero. Good question, absolutely, it's 0%.
When the direction of skew, you say, is the same, wherever you put your power, it is rotated, it's skewed, and that in the direction that it rotates.
No, it actually doesn't matter, because you're allowed to change the direction of this motor either way. So just to make it easy to explain, I went this way, but I can
Yeah.
change the rotation of this motor instantly, and the magnetic field is now going this way. I'm not flipping this around, so it's just skewed. And it's
It's
literally,
just skewed.
yeah, it's starting its thrust at the back end in this case, if it's moving this way, and it's starting its thrust at the front end.
So it'll move, it'll actually move the power from end to end.
Yes, yeah.
In order to,
Yeah, and you just think that's where you get your magnetic field forming. Your magnetic field isn't instantly formed. It's starting here, really big, and radiating down the length of it. And so what you've now got is a nice smooth push for a duration of time, as opposed to all at one time. It's kind of the difference of pushing a car to the gas station. You got 2 ways you can do it. You and your friend can give it the biggest heave on earth and it rolls 10 feet and it stops, and then you run up there and you do it again, or you can give it a nice consistent push and never stop. Efficiency says never stopping is more efficient than push, stop, push, stop, push, stop. It's the inertia, you're overcoming inertia every time you gotta get going again. By doing that skewed, it's that constant even push, continuous, all the time, on every rotor bar, don't forget, right? We're just talking one at a time, but every single one of them has that happening at the same time, which is pretty funky. Now I'm gonna show you something really quick, because none of my electricians know this until I draw it for them. That synchronous motor is ultra cool. You're gonna get power factor, you're gonna get going on power factor. This machine is capable of correcting its own power factor, once you get to it. it corrects its own power factor based on the amount of current you put through the rotor windings. So this right here, that's the rotor windings. As I increase current through that, I change the power factor of this motor. You haven't done power factor yet, right? Today. Really cool. This machine does two jobs. It corrects power factor, which you're gonna see is very important, and also drives a load at the same time. So at McMahon in Taylor, they've got all the steam alternators there. I took my 4th year class down there, that was like 4 years ago. And we walk into the power engineers, that's all class 1, power engineers control center. And we're looking at all the data and I'm like, huh, interesting. I immediately saw with the numbers, they're not doing any work with those alternators. All they're doing is what we call power factor correction. And one of my 4th year students looks at that and he asks the class 1, he's like, how come there's no watts? And the class 1 says, all we do is power factor correction here. And I looked around that room and me and 2 other people knew what he was talking about. That was it. Out of 16 4th year electricians, 14 had no idea what he meant by that statement. And I'm like, that's the difference between why and what. What? Correct power factor. Why? Well, I don't know. So I'll leave you this one thought. I've had engineers in my class, electrical engineers, motor designers, guys that did this for a living before they came to my class when I taught right here. They were actual motor electrical engineers. And one of them told the whole class this one day, he's like, those that know why and those that know what. Those that know what get a job, and those that know why are their bosses. It's that simple. It's like, why do you correct power factor? If you can answer that, you're in the right step. Doing it, the what? Sure, everybody knows that, you can read it in a book. But why you do it, that's what really matters. And so it's kind of cool. All of this stuff, ask yourself why. First of all, why do I need to know? Secondly, why would I, why does it do this? Because once you can answer that, you'll always be able to answer it. You will know it. You don't have to memorize it. You'll actually be able to just know it forever, which is pretty cool.
So all the incoming power goes through the synchronous motor, correct? Or is it, they're generating?
It generates back onto the grid that's feeding it in the first place to actually allow it to offset lagging power factor. And I can quickly draw how it happens. Do power factor, leave this on the board, just this one drawing, and I can come back and show you at the end of the day how it does it. Because you're like, well, that's pretty cool. Once you talk leading, lagging, and all of that, it's really, really simple how it does it. Okay, that's all I got for you. Any questions before I run away?
Yeah, at the beginning you were talking about the Peace Canyon, like the sulfur gas insulator system. What's that called again?
Sulfur hexafluoride. So it's SF6. SF6 shielding for high voltage.
Okay.
That's literally, you look it up, you're like, wow, that is amazing. So the instrument that's involved in that substation is huge. Every section of pipe has an actual pressure switch on it. So if they lose SF6 pressure in any piece of pipe, and they're all just like 10-foot sections with like pre-made 90s, pre-made 45s, all these sections bolt together. If any section loses pressure, the whole substation shuts down. Because losing pressure on that SF6 shielding will immediately result in flashover or an arc to ground. And at 500,000 volts, it's not, it's just boom and everything's gone. Substation is destroyed. So they literally have 100% monitoring all the time. There's like 400 pressure switches just in that substation alone. Ultra cool. And I have a guy in my class, that's what he did for a living in Korea before he moved here. He was an SF6 guy, high voltage SF6 guy. That's actually a job in South Korea. And I asked him about it, I'm like, what? And then as soon as I asked him, I realized why. Here in North America, you can use a quarter section to build a substation and you just use air as your insulator. You get to a really small country with a lot of people, you got 1 acre to build a substation. You can't spread things out 50 feet apart, and so the SF6 shield everything, and it's 2 feet apart. The entire substation takes up 90% less space for the same output. I'm like, absolutely, totally makes sense. It's genius, but ultra cool at the same time. Yeah, I could go on for weeks, I should stop now. Hopefully that helped a bit.
All right, Andy, well, thanks for digging me out of a hole again.
Yeah, you bet. This is the hardest theory there is in electrical. So it's like, yeah, knowing this, it's tough. You don't have to know all of it. Just kind of what we did today. If that made sense, you're good to go. better than the average bear for sure.